Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X, published on November 18, 2025, about 5 days ago. It shows that you can train a single end-to-end model that encodes, decodes, and does diffusion all at once, avoiding latent collapse and still hitting FID scores of 13.44, 6.38, and 4.25, with only 42 million, 118 million, and 205 million parameters, using just 50 ImageNet epochs and no classifier-free guidance. The paper is titled, Diffusion as Self-Distillation, End-to-End Latent Diffusion in One Model. And, as we will see later, the implications for how we design and train future vision generators are pretty significant. Alright, Figure 1 lays out 4 side-by-side pipelines, which makes the core idea behind diffusion as self-distillation very concrete. The left panel shows classic self-distillation, where an online encoder and a slowly updated target encoder produce consistent latent codes for the same bird image. The second panel illustrates standard latent diffusion, which freezes the encoder and only trains the diffusion model on noisy latents. The third panel then unfrees the encoder, showing the naive joint training route that leads to latent collapse. The rightmost panel presents the proposed setup, where diffusion behaves like self-distillation by using an exponential moving average target encoder and a modified diffusion loss. So while Figure 1 contrasted the 4 training setups conceptually, Figure 2 shows how they behave over time on ImageNet. The 5 panels track reconstruction loss in orange and effective rank in blue and green, which measures how many meaningful directions the latent space actually uses. Cases 1 and 2 collapse rank despite low loss, while cases 3, 4, and especially 5 keep high rank, showing that the proposed loss tweaks and strong data augmentation stabilize the representation. Alright, Figure 3 gives a geometric picture of the loss transformation that underpins diffusion as self-distillation. The diagram shows a noisy latent epsilon flowing to an intermediate latent ZT, and then to a clean latent Z1, with arrows indicating both the direct jump and the step-by-step path. The equations state that the velocity, the vector the model predicts, is proportional to the difference between the clean latent and its noisy versions. This means that predicting the clean endpoint latent is mathematically equivalent to predicting the velocity, so denoising and velocity prediction become the same learning task. So after Figure 3 clarified why predicting the clean latent is equivalent to predicting velocity, Figure 4 shows how everything fits into one unified vision transformer. The central yellow bar is a single shared backbone, and the different heads on top and bottom handle latents, diffusion, and images. The 3 green boxes at the top mark the separate training objectives for diffusion, reconstruction, and self-distillation. On the right, a second encoder with exponential moving average weights provides the stable target latents through stop gradient paths. So after Figure 4 detailed the unified architecture, Figure 5 shows what the trained model actually produces on ImageNet at 256 by 256 resolution. The grid contains diverse samples, from birds, reptiles, and spiders, to dogs, cabbages, sailboats, and cityscapes, which illustrates strong coverage of many ImageNet classes. The images look sharp and coherent, with realistic textures and lighting, so the single end-to-end model clearly matches the visual quality of much larger latent diffusion systems. While after Figure 5 showed the visual quality, this table compares that performance against a long list of autoregressive and latent diffusion baselines. The rows at the bottom for DSDS, DSDM, and DSDB use far fewer main model parameters and only 50 training epochs. Despite that, their global FID and sliced FID scores rival or beat many much larger models, while inception scores stay highly competitive. So stepping back, the big takeaways are that a single end-to-end model can safely learn the encoder, decoder, and diffusion process together, and that reframing diffusion as self-distillation fixes latent collapse while staying highly efficient. This points toward unified vision backbones that both understand and generate images. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.